Hello, everyone. Thanks for joining us today. It gives me immense pleasure to host Akhil Bagaria. Akhil is a senior applied scientist at Amazon, working on RL for the Amazon supply chain. He received his PhD in reinforcement learning from Brown University, working with George Conitaris. The majority of his work has focused on the problems of exploration and skill discovery. He was an intern in David Silver's RL team at DeepMind London, where he worked with Tom Schall on goal-based exploration. He studied RL with the goal of creating general-purpose agents that can learn from raw sensory motor data. Prior to that, he worked on the multi-touch team at Apple, where he developed gesture recognition algorithms that are currently shipping on all MacBooks and iPads. He did his undergrad from Harvey Mudd College, where he received the JRR Phillips Award for Outstanding Engineering Judgment and conducted research which included tracking sharks with autonomous underwater robots. Akhil, on to you. The floor is all yours. You can get started.
Awesome. Thanks a lot, Rahul. Thanks for inviting me, everyone. I'm very excited to talk to you about RL, to talk to you about skill discovery. And if there's any questions during the talk, please stop me, ask questions. I would love for this to be as interactive as possible. So as Rahul was mentioning, I am currently working at Amazon, and we're doing some very exciting things here. We're trying to scale RL to make lots of large-scale decisions in the Amazon supply chain. And that's interesting and exciting work, but that's not what I will be talking about today. Today, I'll be talking about work, the other open-ended research that I've been doing for the last few years, and I'm continuing to do now, which is on this question of exploration and planning, right? So how can we get RL agents to discover their own abstractions? So let's dive into it. So everyone has like their favorite way of describing what reinforcement learning is. And I want to tell you about what my favorite way of describing it is. The way I like to think about RL is this beautiful interplay between exploration and exploitation. And when we think about the exploitation piece of RL, I think it looks a lot like other areas of machine learning, right? So we have some given data set, and now we're trying to find patterns in that data set. But I think the part of RL that makes it truly unique is the other piece, is the exploration piece, which asks this question that no other paradigm in machine learning really dares to ask, which is, what data should the agent collect in the first place that would give it valuable exploitation to do in the future? And as central as this exploration question is to the whole RL project, I think that it's also one that we're really, really bad at right now. And so exploration really is both one of the biggest open problems in RL, but is also the key to scaling reinforcement learning, in my opinion, towards achieving much more profound forms of intelligent agents. And I think the way that we currently do exploration, first of all, maybe the most common way that we do exploration is through random noise, right? Like by injecting some randomness into the agent's learning process and hoping that that amount of randomness is sufficient for that agent's exploration perspective. And maybe the second more sophisticated paradigm of doing exploration is through this idea of bonus-based exploration or novelty search. And let's talk about what that is. So if we think about very, very simple MDPs, right? So if you think about tabular MDPs, then we sort of know exactly how we should be doing exploration in these MDPs. And the answer on how we should be doing that exploration comes from decades of really beautiful math in the bandits literature. And what the upshot of all of that research is that whatever reward signal that we get from the environment, we need to add a bonus term to that reward signal. And as long as that bonus falls off in the form of 1 over square root of n, where n is the number of times you've seen a particular state action pair, then you can learn near optimal policies in polynomial time, right? So this is really a profound statement which says that we can do exploration no matter how complicated that MDP is, as long as it is tabular and we can maintain these counts, then we can do exploration by a simple augmentation to the agent's reward, to the agent's reward function. And that's of course really cool. And we would like to import some of that, those characteristics of exploration into larger problems, which cannot be represented in tabular form. So problems that demand function approximation. And so maybe 2 years ago, some collaborators and I wrote this paper, which is, we presented this algorithm called coin flip networks. So the idea here is that when you go from tabular MDPs to continuous MDPs, then you can generalize the idea of visitation counts to the idea of pseudo counts, right? So you may never see the same state twice because you're in a continuous space, but you can learn a quantity called a pseudo count, which behaves like a count. So similar states have similar counts, and the more that you visit a state, then more the count of states that are close to it also increases. And what we presented at this conference a couple of years ago was essentially, and I think it's still essentially a state-of-the-art algorithm, which learns accurate pseudocounts. And if you're familiar with that literature, it turns out a lot of the other methods do not learn accurate pseudocounts, but it also unlocks more sample-efficient reinforcement learning. So for example, here, we're looking at two very sparse reward problems, and we're comparing our method, which is called CFN, to these two other methods. One is soft actor critic, which is just a vanilla model-free reinforcement learning, and R&D, which is another popular way of doing novelty-based exploration. And we're finding that our agent can solve these sort of sparse reward problems in a more sample-efficient way. Okay, so we have a sort of like state-of-the-art, exploration algorithm. So the presentation is over, right? We've solved the exploration problem. But for better or for worse, that's not actually true. And the reason that it's not sufficient is because the world is just simply way too complex to take this idea of novelty maximization seriously, right? So if you think about the room that you're currently in, you could rearrange all the dust particles in your room, and each of those combinations of those dust particles would be a novel state of the world. And you can spend the entirety of your life just rearranging those dust particles. But clearly, that's not really what we mean by effective exploration. So this idea of novelty maximization really is not scalable as an exploration objective. And so that's why today we're going to start to think about what are other ways that we can think about this exploration problem, which of course is central to this RL first paradigm, that does not depend solely on novelty maximization. And my argument throughout this presentation will be that we can organize the exploration of the agent through the lens of abstraction acquisition. So if you're an agent, you're interacting with an environment, and you're doomed for that interaction to be in the low-level MDP, right? So you observe low-level observation, pixels on your retina, sound on your eardrums, and you have to interact with the environment through your motor torques, right? So muscle actuations. And yet, we can think about, for each different task that the agent has to solve, abstracting that state space into an abstract state space, and that action space into an abstract action space, and then doing planning in that smaller abstract version of the MDP to solve each of the tasks that the agent might be interested in. And so the core thesis I have for this talk today is that that effective exploration that we're really after can be achieved when this agent is intrinsically motivated to acquire an abstract and plannable model of the world. So the exploration objective can move away from randomness or novelty maximization to the drive of acquiring an abstract and plannable model of the world. Now, this conversation about abstractions tends to be very loosey-goosey often in AI. So we're going to ground it in the options framework. And if you're not familiar with options, they're essentially temporally extended actions, right? So an option is composed of three elements. First is the initiation set of an option, which is the set of states from which you can begin that option's execution. So for example, if you had an option to open a door, then all the states in which a robot is close to the door would be the states inside that option's initiation set. Then the second element is the termination region of that option, which you can also think of as the sub-goal of the option. So those are the states in which option execution stops. So in the example of the door, those would be the states in which the door is actually open. And then the final piece is the policy of the option, right? So that's the closed loop controller that is taking the agent from the states in the initiation set to those in the termination. And so the field of hierarchical reinforcement learning has known for a long time that when an agent is given well-designed options that can significantly accelerate both learning and planning, and I guess this has been known for over 25 years now, and we recently wrote a survey paper with some folks at University of Alberta and Mila, which I encourage you to check out. But the core question has always been, and continues to be, but how can the agent acquire these options or these skills autonomously from interaction with the environment? So this is known popularly as the skill discovery problem or the option discovery problem. So today what we're going to be talking about is how we can first discover options in a simplified setting, then how we can discover both options as well as the complementary state abstractions in more complicated problems. Then we'll start to generalize that more and more towards high-dimensional observation and state space, observation and action spaces. And finally, we'll talk about worlds which have a multitude of very complicated goals that the agent might be interested in pursuing. All right, so one step at a time, let's start with a simplified version of the problem, right? So now let's imagine that you're controlling this little robot, and its entire goal in life is to reach that goal, which is shown as that black flag. And we can ask, even in this simplified problem, what do good options look like, right? How should an agent discover useful options in this goal-reaching task? And so this was the first paper that I wrote during my PhD. The paper is called Option Discovery Using Deep Skill Training. And the core idea is that options that an agent discovers should have the property of sequential composition, meaning that once an agent executes a particular option, it should be able to execute another option, which then brings it closer to its goal. So we'll take a look at what that means. So here, again, the goal of the agent is to reach this black flag, right? And so we can say that the termination condition or the sub-goal of the very first option that the agent has is known. It is to reach that goal. And so now we can ask, well, what are the states in the environment from which that agent can execute a single policy and reach that goal with high reliability? And we'll call those states in the environment the initiation region of that first option. Now we'll go into how we can learn that initiation region, but for now, let's say we have some magical oracle that allows us to learn it. And now we can say that the sub-goal of the second option is the initiation region of the first option, because we know that as long as we can get inside the initiation region of that first option, we'll be able to complete the remainder of the task with high probability, right? So this should be sounding a lot like a divide and conquer approach to these goal-reaching tasks. And now we can learn what are the states in the world from which that second option can achieve its own sub-goal with high reliability. And we can continue this process recursively backward from the goal until the start state of the MDP is inside one of the option's initiation regions. So at the end of this process, what we've essentially done is that we've broken up this problem, which might have thousands of primitive action executions, into, in this example, a series of 3 sequential option executions. And by executing these options one at a time, the agent can reliably get from its start state to its goal state. So how does the agent learn these initiation sets? So imagine that this yellow star is the subgoal of an option. And the way that the agent learns the initiation set of that option is through trial and error. So it continuously executes that options policy from all these different states in the world. And from all the states from where that option execution is successful in achieving that goal, we label those states as positive examples. And all the states from which that option execution is unsuccessful, we label those as negative examples. And then we can fit a simple binary classifier. And then once you fit that classifier, for any given state, you can ask, what is the probability that if I initiated my option policy from that state, I'll be able to achieve that option subgoal or not? And I guess if you don't like to think about this initiation set learning as a classification problem, there's also an equivalent or perhaps a better way of looking at it from the lens of general value functions. And we had a paper on how to frame it as general value function learning. So now I'll show you some fun videos, hopefully, of the agent executing some learned options. So here we're trying to control this little ant robot that has to go from the bottom of this maze to the top right of this maze. And it has a sparse reward function. So it only gets a +1 reward when it gets all the way to its goal and 0 everywhere else. So this is obviously a hard exploration problem. And the ant changes color every time it's executing a different option that it discovered during its learning process. And you can see that the agent has sort of broken up this long horizon problem into a sequence of these shorter option executions. I'll pause very briefly if there are any questions so far. Yes, hi. Oh, you're muted, I think.
Can you hear me now?
Yeah, I can hear you now.
Thank you so much for your talk. And if you would please just could you clarify where this idea of an option, which looks like a collection of states, basically fits with the normal, a normal reinforcement learning workflow. I guess what I'm it's not exactly clear to me how it fits together with the normal workflow.
Sure. Yeah, that's a fair question. Okay. So when we think about reinforcement learning, right? So our favorite formalism is that of an MDP. An MDP has states and it has actions. And those actions only last a single time step, right? So that's the basic MDP premise. Now, options provide a bit of a spin. So it says that the actions that you have may last more than a single time step, right? So they might last they might exist over temporally extended periods of time. And over that period of time where that option is executing, you can think of it as being a low-level controller that is sort of taking you from the beginning when you started executing that option towards its end. So it's really a simple modification to the MDP tuple, where instead of having fixed single time step actions, you now have variable and temporally extended actions. And the reason we want that is because this temporal abstraction is exactly that. It's an abstraction, right? It allows you to reason at different time scales. It allows you to think more abstractly about the problems that you want to solve.
So normally when you're, for example, you're doing something like Atari, reinforcement learning for Atari games, you take the state and the network produces an abstract state, and then that abstract state produces your actions and so on. In this picture, exactly how does this option get produced by the network, I guess?
Yeah, so first of all, the way to think about it in like the DQN, I like the Atari example. The way to think about it in DQN and Atari is you have observations going in, and then usually if you go back to the DQN days, we stack 4 frames, right? And we say that that's our state representation. But the other trick that we do is we say that once an agent picks your neural network outputs an action, that action is going to last for 4 time steps, right? And we're going to execute them for 4 time steps and then tell you what that next state is. So you can think of that action repeat as a very simplistic and a very naive option, right? Because technically, you should have only executed that action for a single time step. The reason we did it for 4 time steps is because it eased the learning process. So really here, what I'm asking is there a generalizable way that we can figure out what these temporal abstractions should be for any given problem without us having to hard code this hack of repeating actions for 4 time steps at a time? All right, great questions.
Thank you.
Yeah. So we sort of looked at this algorithm called deep skill chaining, which when you're given a start state and a goal state, you can sort of decompose that problem into a series of subproblems, each of which can be thought of as an option. And you can do a similar thing where if you have multiple start states and you're trying to funnel all those start states into a goal state, you can organize your options in the form of a tree. But, and I think a more interesting version of the problem now is if you could be asked to start anywhere in your MDP, and if you could be asked to go anywhere in the MDP, then how would you organize the options that you have? And the answer has to be that you have to organize your options in the form of a graph, so that between any arbitrary pair of start goal states, there's at least one chain that connects them together. And this was the topic of a paper that I wrote a few years ago at ICML. So what does that mean? What is the skill graph? So like all good graphs in computer science, it's a weighted and directed graph. And the nodes of this graph represent option termination regions or option subgoals. And the edges of the graph are actually these option policies. So contrast this with the graph view of an MDP, where individual states in that MDP appear as vertices or nodes in that graph, and the edges correspond to single time step primitive actions. Whereas here, our nodes are these abstract states that the agent has discovered for itself, and the edges, instead of being these single time step open loop actions, they're entire closed loop policies. And so that's what a skill graph is, but why would we be interested in building such a skill graph? And my favorite reason is for exploration. So we're going to see that the agent is going to acquire the skill graph in a way that the coverage of that graph is going to grow over time towards larger and larger portions of the MDP. And then at test time, when the agent is given a goal, then if that goal is inside the region that is spanned by the graph, the agent can simply use planning to reach that goal in zero-shot way. Or if it's outside the graph, then the agent can plan to the nearest node in the graph and then switch to learning for the last bit. So the algorithm for acquiring this graph is very simple and has 3 high-level steps, right? So imagine that these blue nodes represent the current state of the graph. And the first step of the algorithm is to identify a goal region, which is shown here in red, which is outside the graph. Then the agent does planning to the nearest node in the graph, which is shown here as green. And the red arrows shows the plan over options that the agent executes in order to get to that green node. And then the final step is going to be extending that graph from that green node towards that red node. And in that process, adding more nodes and edges in between. So we'll go into more details on each of these steps. And the agent is going to continually sort of switch between 2 modes. One is that it's going to try to expand the coverage of this graph in the MDP. And then the second one is that given some graph, it's going to try to increase the probability that it can get between different regions of that graph. So that first step of expansion, I think, is a lot more interesting. So I'll go into that now. So again, imagine that this is the current state of your graph, right? So all of these nodes, again, are these abstract states, and the edges are option policies. And the agent, the red circle right here, this is the starting node of the agent. And now the exploration question here is that if I told you, like, you get to add one single node to this graph, but your objective is to add that node in a way that in the end, you maximally increase the coverage of the resulting graph in the state space. Where would you add that edge? And that seems like a very complicated question, right? But the answer to that question ends up being surprisingly simple. And the answer comes from decades of research in motion planning. And the answer is just random sampling. So what does that mean? So the first step that motion planning tells us to do is to randomly sample a state from the state space. So here that random sample is shown as the blue star. Then you identify the nearest neighbor inside the graph, which is shown here as the green node. And now you extend the graph from that green node towards that random sample that you got in the first step. And the claim is that if you just do this 3-step procedure, then you will have a graph or tree acquisition process that automatically causes this graph to expand towards unexplored parts of the state space. So whatever parts of the state space where you don't have a lot of nodes, your graph will automatically expand towards those frontiers. And that's exactly the kind of property we want our exploration algorithms to have. So this property in motion planning is known as the Voronoi bias, which says that if you commit to this 3-step process, what you're actually doing is that you're picking a node for expansion in the graph that has Voronoi bias, meaning that in expectation, you end up picking nodes that have the least number of nodes around it. So over time, if you keep running this algorithm, you'll keep getting more and more coverage of your state space. And that coverage, remember, corresponds to mastery over the environment, right? Because wherever the agent has this graph, it can use planning rather than doing reinforcement learning. And planning, as we know, is a lot more sample efficient and generalizes to long horizons than just flat model-free reinforcement learning. Okay, so some more mechanics. Once you've identified this nearest node in the graph, you can use planning with your existing options to get to that nearest node. And once you get there, you execute a low-level policy that moves in the direction of that randomly sampled goal from the first step. Now, it could be that you don't get all the way to that randomly sampled goal. Maybe that random sample was a completely infeasible goal to have in the first place. But that's totally fine, because wherever it is that you end up after those case steps of policy execution, you plant a flag there and you say, okay, this is my new node in the graph. And now you keep going back to that green node, and now you run that deep skill chaining algorithm that we talked about in the previous part, and you add as many nodes and edges as you need to reliably get from that green node to this new node that you just discovered in the graph. Right? So by continually going back there and running deep skill chaining, we've added a new portion to the graph that now has given us this reliable connection from existing portions of this graph to this new node that we just added. And now that new node, again, becomes a part of the state space that we can use planning with existing options in order to get to. Yeah, Reza.
Thank you. So how do you control the number of these nodes? It looks like, for example, is there such a thing as deleting a node and adding a new one, or things like that?
Yeah, great question. So, how many nodes should we add between the green node and the new node that we just found? And I think the cool thing is that here you don't pre-specify that, right? Because think about different problems requiring different number of options. What I mean by that is, so if you have a really simple robot, right, like maybe a point mass, then you can get from one node to another node that's really far away in a single option execution, right? And you can do that reliably. But now if I give you a really complicated robot that has unstable dynamics, you're not going to be able to do that in a single option execution. You're going to have to break that up into these different subproblems in order to get from the green node to the black node with high reliability. And that's what deep skill chaining is doing for us here. It's giving us adaptively as many nodes and edges that we need in order to reliably connect that new node to the existing portion of the graph. Great question.
Thank you. Thank you.
So now let's look at what the process of evolution of this graph, which is pretty interesting. So now we've dropped this little ant robot in this large maze. So the ant starts at the bottom left of this maze, and during the exploration phase, it's just sort of trying to acquire this graph, right? So that's this exploration objective. And you can see that as training time progresses, the graph sort of incrementally grows outward from the state space towards unexplored parts of the state space. And now you can say at test time, I'm going to give this agent some randomly sampled goals that it did not see during training time. And it's got to use the options that it's discovered in its exploration phase in order to reach those goals. And so the goals will be shown here as red spheres. And again, the ant will change colors every time it's executing a new option that it discovered during its exploration phase. And you can see that even though these goals are really far away from the start state, the agent is able to get to them with high reliability because it's using this combination of planning with its options in order to drive its learning process. And here are some quantitative results where we compare this algorithm against a bunch of other model-based and model-free algorithms, including hindsight experience replay, which is quite popular. And I think the only interesting thing from these plots is that as you increase the sort of complexity of the environment, so when the environment is really simple, right, like in this bottom left ant feature, then pretty much like most algorithms are giving you a reasonable level of performance. But as you start to increase the complexity of the problem, the sparsity of the reward function, and the sort of unstable nature of the dynamics itself, then you can see that our algorithm is able to maintain its level of performance, perhaps because it is acquiring the skill graph and planning with it. Okay, so hopefully that was clear about what the skill graph is and how we go about acquiring it. But now I'll tell you all the ways in that we are cheating, right? All the assumptions that we had to make in order to acquire this kind of graph in an automatic way. Yes, so there's a question in the chat, which is, isn't this a sparse reward setting? That is absolutely correct. So this is a sparse reward. So at test time, you get a +1 reward when you reach the goal and 0 reward otherwise. So maybe the question was about these plots. So these plots are measuring your average success rate. So if I give you 100 goals at test time, 0.8 means that you reach 80% of those test time goals within the allotted time budget.
Are you also giving some reward if the agent reaches those sub goals?
Right. So those rewards are internal to the option, right? So the agent has constructed its own sub goals, and it to drive the learning of the option policy itself, that option policy gets its own sub goal reward when it reaches its own sub goal.
All right, makes sense.
So you can think of those as intrinsic rewards.
Right.
All right, so what are some of the assumptions that we're doing that are not cool? The first one is the state sampling. So the very first step of the algorithm, I said you can sample a state from the state space. But what if your observation space is the space of all images, right? What does a random sample from the image space even mean? And why would that be useful in guiding behavior? And some other ones are like this notion of finding the nearest node in the graph sort of relies on this idea of having some smooth metric over your state space, which again may not exist in high dimensional observation spaces. So now we're going to talk about how we can lift some of these assumptions to again build a similar graph, but one that we can do not just in these sort of smooth state space problems like in Mojoko, but also in more higher dimensional observation spaces like those with images. So this plot here is showing how we were acquiring this graph in this skill graph algorithm, right? Which is that it relied on first sampling a random state from the state space and then pulling that graph towards that random sample. But now instead, what if we thought about it in a different way? What if we thought about it instead of first sampling this random state and then pulling the graph towards it? What if we thought about it as identifying a node that already exists in the graph and then pushing that graph outward from that node instead? And what that means is that we're going to assign a score, a utility value, to each of the nodes in our graph. And wherever that utility value is highest, we'll pick that node for expansion. We'll get to that node, again, using planning with our existing options. And then we will execute a low-level exploration policy. So from the very first part of the talk, the novelty maximizing policy. But instead of doing novelty maximization globally everywhere in the state space, now we're doing local novelty maximization. We're doing more targeted exploration because we're locally exploring in the region of that expansion node that we identified in step 2. Right. So the detail here is that the way that we score each of the nodes in our graph is by asking the following question, which is that if I executed a low-level exploration policy, like a novelty maximizing policy, how much expected sum of intrinsic reward would I accumulate if I started my my low-level exploration process from that node, right? So thankfully, those are exactly the semantics of a low-level exploration value function. So we can use the coin flip networks that I talked about in the first part of the talk to assign a score to each of the nodes in our graph, pick the node with the highest exploration value, and then unroll or roll out our low-level exploration policy. And then when we roll out that exploration policy, whatever state that we encounter that has the highest intrinsic reward, we can say that that state is the new node in our graph. So let's look at an example of what that ends up looking like. Oh, by the way, you can also find this in a recent paper that we published at RLC. So this is an interesting puzzle. This is called Sokoban. You're controlling this little green alien, and the goal is to get all the boxes in their respective, all of these yellow boxes into their red squares. So this is a combinatorial sort of search problem. And again, you get a +1 reward at the very end when you solve the whole puzzle. So it's a difficult exploration problem. And if you just did pure low-level exploration, you're looking for this needle in a haystack, which is very difficult. But the way that the skill graph algorithm does its exploration is that it says, okay, I know that when 2 of the boxes are already in its place, I know how to get to that state. So how about I plan with the options that I already have? So use my model and my planner to get to that state and then do low-level exploration. So if you do low-level exploration from that state where 2 of the boxes are already in their corresponding locations, then you're much more likely to stumble upon that needle in a haystack, where you get that 3rd box also in its corresponding location. Okay, so it's sort of a more targeted way of doing exploration where you're interleaving exploration and planning in this smooth way. You're constantly doing planning to reach the edges of your existing model. And then once you've reached the edges of your model, then you do local exploration and then keep expanding that model as you go forward. So we also tried this in Montezuma's Revenge, which is a fun Atari game. And what you see is that the agent learns these options. So the first option that it always learns is to go and kill itself on the skull. So once the skull is out of the way, it then has an option to go and pick up the key, and then a third option to open the door with that key in order to get out of the first room. And this works in more than just the first room of Montezuma. So it's sort of like built incrementally, expanded this graph so that it spans about 8 rooms in the game. And if you compare that with just flat model free RL, which is DQN, then that is unable to leave you in the first room of the game. But this sort of intrinsic drive to build this graph, plan inside the graph, and then do local exploration outside of it allows the agent to explore about 8 rooms in the game. Now, of course, there are like 24 rooms in the first level itself, so we're still far away off from solving this game, but so we still have some work to do. Okay. Yeah, we have some quantitative results as well, where we compare against just flat model free RL, which is called R2D2, and novelty maximization, which is just CFN. And we're seeing that the new intrinsically motivated skill graph is able to beat these algorithms pretty consistently. All right, so we talked about skill chaining, which was for single start state, single goal state. We talked about skill graphs, both when you have a smooth state space with a metric, and we also talked about intrinsically motivated skill graphs for high dimensional observation spaces. And now we'll talk about scaling this even further. So a lot of this work was done with my mentor at DeepMind, Tom Schall. And the basic idea of this part of the talk is to think about exploration beyond coverage. So what does that mean? So if we think about the way that we are talking about exploration, whether it's novelty maximization or whether it's the skill graphs I just talked about, the underlying objective that we're, sorry, is that a question?
Yes.
Yes, go ahead.
Hello. Yeah. Hi. I just wanted to know, does this ever exploit the environment
I'm
in
sorry,
any way?
can you repeat?
Am I audible now?
Yeah, can you repeat your question?
Yeah. So I was saying, does this ever exploit the environment, its environment?
Yeah, it does, right? So in these examples, so here on the y-axis, we're showing the extrinsic reward. So what it's doing is that it's building its graph, and then once it starts to get extrinsic reward, then it starts exploiting that in extrinsic reward. But before it sees that extrinsic reward, then it's guided intrinsically to build that graph and expand its coverage in the state space.
Okay. Thanks.
Yeah. All right. So coverage is a bad objective for exploration, and here's what I mean by that, which is, we looked at how you can sort of acquire a graph in this big ant maze. Right now, my question for you is that if I replace this little ant robot with a more complicated humanoid, does that qualitatively change the exploration problem? And my answer to that question is no. Like, it changes how, like, what the sample complexity would be to learn each of the options policies, but it doesn't qualitatively change the exploration nature of the problem, because everything in that problem is still reachable, right? Maybe it takes you a lot of samples to figure out how to get to the other extreme of the maze, but eventually you can get to all of those points. And everything in that environment is within your control. But the real kicker is that the real world is not like that. The real world is not like Majoko or Atari, where in fact in the real world, most of the goals are unreachable, and most of the things in the real world are also uncontrollable. So for example, there are like a lot of goals in your head right now that are simply unreachable, and there are other agents in the environment which you don't have perfect control over. And thirdly, this idea of coverage is really a bad one, because states in the real world can never be revisited. And I don't mean this in sort of a approximation sense. Like I don't mean this in a like, oh, our state space is continuous and we only have finite precision in our computers and in our brains, so therefore we cannot revisit the same state again. No, I mean this in a very profound sense, which is that this particular state, this particular time cannot be recreated in the future, right? And when I talk about controllability, I also don't mean this in a noisy TV sense, which I think RL folks often get fixated upon, because, and the idea there is that if there's some random noise, then the agent might be, distracted by that random noise and attracted to it, and getting all of its exploration signal from there. While that is true, it's also the case that not all things that are uncontrollable should be ignored or can be treated as distractors. For example, what the president of the United States does is mostly out of your control. And yet what they end up doing impacts what the optimal policy would be for you, right? So it's not always the case that things that are out of your control are things that we can treat as distractors, which is what I think the majority of the literature around controllability has done so far. So when we think about exploration in these more serious problems, then I think we should turn to the masters of exploration, which are children. And imagine a child that's sort of like playing around, and it does something random, and it causes a loud sound to be made. And it's like, aha, I got a loud sound to be made. How can I recreate that sound with increasing reliability in the future? And when it tries to recreate that loud sound in the future with its toy, it doesn't care about what the exact weather is outside or the lighting conditions or what the state of the other toys are either, right? It's just focused on that one toy and about creating that loud sound from that one toy. And so we can take that as inspiration for an exploration algorithm. And we can say that once you are executing a trajectory, you're going to sort of see all these states in that trajectory with differing amounts of novelty. And so Sn here is the state in that trajectory which has the highest novelty, so the most interesting state that you saw in that trajectory. And Sb is the most boring state that you saw in that trajectory. And now you can ask, well, I can see that 2 out of 3 of my features changed in going from the most boring state in that trajectory to the most interesting state in that trajectory. Which of these features actually explain that difference in novelty? Right, so that's what we did in this particular paper, where we said that we can take these 2 states and produce counterfactuals. So we can say, if we were to replace the features of the most interesting state one by one with that of the most boring state, at what point does the novelty of the resulting counterfactuals drop substantially? So when that novelty does drop substantially, it means that that particular feature that we modified was very important in explaining that difference in novelty. So for example, in the scenario of the child playing, would that child have found that loud sound to be interesting, even if the weather outside was cloudy, or even if it was nighttime instead of daytime? And the answer is yes, right? The thing that it was attracted to was the loud sound that it made. And therefore, we can identify that loud sound itself as the interesting feature and learn a classifier that only pays attention to that particular feature and ignores everything else. So here's an example of what that looks like in this mini grid problem. Here, the state sort of has all these different factors, right? It has this red triangle that you're moving around the grid. It has this purple key. And it has all these different doors and this ball. But during the exploration process, the agent is asking, well, I saw a state that was very novel, but in the plot on the very left, the thing that was very interesting about that state was not the state of the key or all the other doors. It was just where that agent was in that particular point in time, and the fact that this yellow door was open for the first time. And similarly, in the second one, it finds that, oh, the thing that was interesting about that state was that this key was in a different location than what I'm used to seeing, right? So it learns an option subgoal, which only pays attention to those particular features and none of the other objects in that environment. So it doesn't care what the state of all these other doors are. And so what you end up with in this way is option subgoals, which are a lot bigger, a lot more abstract than the option subgoals that we had earlier, which were targeting individual states. And so we've tried this on some sparse reward problems again, and we can see that both that you're able to get more sample efficient learning, but also that you're able to do this with a lot fewer options than you were in the past, because each option is sort of responsible for getting you to a much larger region of the state space than if you were to resort to state coverage. Okay, so I think I'm running out of time. So for this part of the talk, all I wanted to say is that when there's a lot of different goals in your goal space, we shouldn't be trying to learn a policy, a goal condition policy that can reach all of those goals. But in fact, we should have this additional filtering or sampling step, which prunes out goals that are implausible. And what I mean by implausible are goals that are uncontrollable and unreachable. And then sample goals that are desirable, meaning that they are relevant for the distribution of tasks that that agent cares about, as well as being novel. And if you were to filter out the space of all possible goals using those metrics, then you end up with a goal condition policy that's a lot more useful and a lot more performant than if you were to not. So here I just have some details about how we can learn which of the goals in your space are controllable versus reachable using the ideas from general value functions, but I'll let you read the paper for this for more details. And once you know which goals are plausible, you can sort of assign desirability scores to your goals based on reward relevance and novelty, and sample goals from that distribution. And once you have the sort of both plausible and interesting goals in your goal space, there's another fun thing that you can do, which is try to recombine goals to create new goals, right? So you can say, for example, I have a policy that can pick up a key with high reliability, and I have another policy that can get to a door with high reliability. Now I wonder if I can create a new goal, which is the combination of those two goals, which means that I both have the key and get to the door with the key, right? And that itself can be treated as a new potential goal whose plausibility and desirability you try to eke out in the future. So you can sort of, in this constructivist way, ask increasingly complicated questions. And we'll see a fun example of this here. So this is a fun little game called Baba Is You. And the goal here is to create a rule which says wall is win. And once you create that rule, you can go to this little wall here on the bottom right, and that's going to be the goal. And then you get your +1 reward at the end. And so the way that the agent is doing its exploration here is that it's asking questions, right? So first, all of the questions that it's asking are about navigation. So it's all asking like, oh, can I get to location A or can I get to location B? And then eventually, for the first time, it moves around that block of which says wall. And now it has questions about that wall's movement. Like, oh, I wonder if I can move that wall to location A or location B. And so by doing this, it's sort of building this implicit curriculum where it's first taking care and mastering the goals in the goal space that are easy, and then moving on to goals that are very difficult. And if it's by guiding its exploration in this way, it's able to solve sparse reward problems. So I know I threw a lot of information at you, but to sort of recap what we talked about, I think if you don't remember anything from this talk, the main message I have for you today is that I really want us as a field to stop thinking of exploration as coverage, right? I want us to think of exploration or randomness or coverage. And instead, I want us to think about exploration as this intrinsic drive to learn abstract models of the world. that you can then use for planning. We first looked at this algorithm called deep skill chaining, where an agent discovers sequentially composable skills to solve single task problems. Then we looked at the skill graph algorithm, where the agent is also learning the complementary state abstractions for the options that it's discovered in order to reduce large continuous MDPs into small discrete graphs, which it can do planning very easily over. This skill graph had a sort of high-level exploration objective where the graph continually and automatically expanded from the start state towards unexplored parts of the agent's frontier of experiences. And then we sort of took this big world perspective, right, where we said the vast majority of goals in an agent's goal space are in fact unreachable, uncontrollable, or undesirable. And so we want to find a subset of those goals that are useful for driving the exploration of the agent. I think my final message here is that I think it's a very interesting time that if you are interested in sort of scalable experience first approach to AI and to RL, I think that the discovery problem is one of the core questions to work on. And I hope that it's as exciting to you as it is to me. And that's all I have for you today. Thanks. And these are all my collaborators.
Thanks for interesting, insightful talk. Very interesting. I hope there are a few questions. Probably we can take it offline. I think he is happy to reach out through email, I guess, if you have any questions.
Yeah, absolutely. Feel free to send me an email, shoot me a message on Twitter. Always love to talk about all things RL.
Yeah, great. Thank you, Akhil. Thanks for joining us. It was great.